St. John's in Annapolis, graduating in 1932. Then I did my doctorate work at Princeton under H.S. Taylor. I finished that in 1935 and stayed an extra year as a postdoctoral fellow, which in those happy days, a postdoctoral fellow was an independent person rather than a slave. I taught for 3 years at Trinity College in Hartford, Connecticut, from 1936 to 1939. I married Elise Frank from Hartford, came to Northwestern in the fall of 1939, and they've never been able to get rid of me. So I'm still here.
How would you describe Sir Hugh Taylor?
Well, Taylor, of course, first he was a very busy man. He had usually lots of things going on. But nevertheless, he came through the laboratory every day once. And the standard graduate student view was that if you could show him a graph, he would be happy. So one should always try to have a graph of the last day's results.
Who were some of the people that were at Princeton at the time you were there?
Well, John Turkovich was a year ahead of me. Back to your question. John Turkovich was a year ahead of me. Kiyoshi Morikawa worked for a couple of years at the next desk. He was over on a sort of postdoctoral fellowship, although he hadn't a doctor's degree at that point. He worked for the South Manchurian Railway. And he was the person who did the first isotopic exchange between deuterium and alkanes, methane, ethane, and propane reacting on nickel catalysts. There was a German postdoc who was on the other side of me for a year named H.W. Kohlschutter. Same room at one point there was a man generally called Sunshine Bearer. A Smith was there. I'm thinking of the ones in the room. That was it, I think.
Now, this must have been an awfully large room.
It was a big room. I was in the room a little while ago and I could still see one trace of my activity. I was measuring the absorption of carbon monoxide at that point. I started off with carbon monoxide absorption, hydrogen absorption on zinc oxide. These didn't lead to anything particularly interesting, so Taylor got me to change to measuring hydrogen chemisorption on chromium. But in the carbon monoxide period, I was generating carbon monoxide by a sort of kip generator in which you dripped formic acid into hot concentrated sulfuric acid, decomposing to water and carbon monoxide. Okay, what do I do with the carbon monoxide? With no hood anywhere near. So I took a cork borer, carborundum powder, and carefully drilled a hole, small hole in the window pane, and put a tube out. Taylor came around, looked at it, and said, "Who did this?" "I did, sir." He looked at it, he never said anything more. When I wasn't using it, I just put a cork in it. And some years ago, I happened to be in the lab, and the cork was, and the hole was still there. Probably the only trace of my period.
Now, this was Taylor's entire group at that time?
No, he had other people. For example, when I first came there, P.W. Selwood was there as a postdoctoral fellow. He was running a small factory which made deuterium by electrolysis, selective electrolysis of water. And Taylor also did work in photochemistry as well as catalysis, and he had a couple of people working in photochemistry.
How did Taylor interact with graduate students and postdocs?
But Taylor was rather formal. And reactions were primarily scientific. With most people at any rate, with me it was that.
So he didn't have you to his home, or?
Oh, in those days it was customary to pay a social call. So a couple of times I paid a formal social call and was served tea of a Sunday afternoon. Princeton that day had a lot of such affairs where you went to tea. And that was about all the social contact I really ever had with Taylor.
How would you compare the graduate courses then to graduate courses now in chemistry?
Well, at that point, it was customary for graduate students to take more courses than they take now. So I took one in advanced in organic, thermodynamics, statistical mechanics, took a couple of quantum mechanics with Henry Eyring, and when I arrived, they decided, coming from a small college on examination, that I really should take the elementary physical chemistry at start, which I did in addition to the other things.
And which undergraduate school did you go to?
St. John's in Annapolis. That was a small college, but the reason I got to Princeton was because the first year I was there, Everett S. Wallace was teaching at St. John's. He'd been there several years, but after my freshman year, they offered him a position at Princeton, where he was a well-known inorganic chemist, particularly in the area of molecular rearrangements. He got me into Princeton.
And what got you interested in chemistry to start with?
Chemcraft sets. I must have been given the simplest Chemcraft set for a Christmas present once, but I always, as far as I know, I can't remember when I didn't have some interest in this kind of thing. So I had myself in our basement a little chemistry laboratory in which I performed a number of dangerous experiments. I even set out once to make nitroglycerin. When it started to fume heavily, I got nervous and carried it out in the backyard, but nothing happened. I had a friend who became rather famous one day. We were close friends, about the age of 13 to 14. And we conducted all kinds of reactions with explosions. We made gunpowder, we used potassium chlorate, sulfur, and charcoal, blew up various things, fortunately never ourselves, so it must have been close. Bruce's father, later Commodore McCandless, had given him a lathe, and we turned out models of the cannon in the Naval Academy, and we bought at Dawes Hardware Store. In those days, a pair of 13-year-old boys could go into the hardware store and buy a can of DuPont 4X gunpowder without any complaint. It was still then used by old-fashioned duck hunters who insisted on loading their own shells. And we drilled them for 22 slugs, and then we would go down to Spa Creek and fire them off and see how far we could project a 22 slug. And none of these things, I think, would be highly recommended, but somehow we survived them. Bruce McCandless became very famous one evening in the night battle of Sabo Island, when he was on, I think it was the USS Louisville. And the American fleet got between two Japanese lines, ships, and firing started. Sorry, it wasn't the Louisville, it was the USS San Francisco. and a Japanese shell hit the bridge. And when the smoke cleared away, the admiral was dead, the captain of the ship was dead, the executive officer was dead, the gunnery officer was dead, the navigating officer was dead, and Bruce McCandless wasn't. He was essentially uninjured. And he was just now the senior officer on the bridge. Well, the first lieutenant was senior to him, but when he got hold of the first lieutenant said, look, if this ship is to be kept afloat, I gotta stay at work. The first lieutenant's damage control officer. And so Bruce took over the fleet and extricated it. When he got back to San Francisco, President Roosevelt had flown out to present him as Congressional Medal of Honor and a jump promotion. So at that one particular day, he was a very famous person.
I take one on to Annapolis.
I'm sorry?
Did he go to Annapolis?
He had been to Annapolis. His father was a naval officer. He went to Annapolis.
And how large was your chemistry class, undergraduate?
Oh, probably, I can't really remember. I do remember one, of course, in advanced organic chemistry, which consisted of 2 people, but ordinarily they would probably have been 15, 12 to 15, I think.
And what was your impression on arriving at Princeton?
Well, I was interested in it. It was a new experience for me, coming from a little small college, you might say a country college. And you know, I was confronted with a large place. It seemed to me large. It really isn't. I referenced other universities, but it had a lot of handsome Gothic buildings and all kinds of activities I'd never seen before.
And how did you come to select Taylor as your research professor?
I'm not really sure that that can be answered. There were a certain number of possibilities, and I decided on Taylor, probably for not entirely logical reasons. He was the most famous person. That might have influenced me. But what he was doing seemed to be of interest.
Did you have to go talk to him for the selection procedure, or what was the selection procedure?
I think all you did was to say, here I am.
How did Eyring and Taylor interact at that time?
Well, you know, a graduate student doesn't really see much of that. And I saw a little of Eyring. He would like me to have become a theoretical chemist, which fortunately I didn't do, because I don't think I really had the talents to do it. But he had assigned in a class a certain problem, and I had solved it. And Eyring said, oh, this is good, we will publish it. But then a few days later he said, oh dear, I discovered that it's already been published. Well, it had been published by a rather famous man, so it wasn't too humiliating.
Who was the famous man? Do you remember?
I could dredge it up, but it's not on the tip of my tongue right now. One of the well-known earlier quantum mechanicians.
Did you interact with Eyring other than in the course?
Well, you could talk easily with Eyring. Eyring always, I think, liked to talk to graduate students. I saw him at a meeting in Houston of the Welch Foundation just before he died, in which he came in there on a wheelchair, insisting on attending the Welch board, of which he was a member. And he was very deliberately seeking out younger students, talking to them like a Dutch uncle. So you could talk to Eyring.
Now, at that time, did he have an independent research group?
Yes, oh yes.
Did you interact with Selwood at Princeton?
We overlapped, I guess, was it, I can't now remember, it was 1 or 2 years. I knew him personally and so on. I didn't interact with him scientifically. And of course, when I got to Northwestern, here he already was.
Well, did Taylor have you come to his office, or did he make tours of the lab?
Mostly he made tours of the lab. If you wanted to have something special to talk with him, you had to make an arrangement with your secretary, Miss Darcy. And so that would happen periodically. He would never refuse you, or he might put it off, but ordinarily he came to the lab.
Who are some of the other faculty members that you recall from that?
Well, there was Everett S. Wallace, who I saw personally quite a lot. He had been an acquaintance of my family in Annapolis, and so he was sort of behaved like an uncle to me. He would have liked me to become an organic chemist, but I'm afraid I disappointed him when I became a physical chemist. There was Robert N. Pease, who was a physical chemist. One of the more interesting people was an elderly retired professor who I would talk to several times, and he told me about how he had looked through Bunsen's original spectroscope when he had visited Bunsen. He'd done his PhD in Germany. There was Roy W. McKay, an inorganic chemist, he was continuing every day. He came into the laboratory, took off his coat, and went to work. And he was working on sulfur complexes of things like arsenic and antimony, doing work which had been fashionable 30 years before, which would probably become fashionable in another 30 years, but it was rather out of the mainstream at that point. There was Professor Paxu, who was an organic chemist. At Princeton, you didn't get, in those days, you didn't get grades in graduate courses. You just signed up for them. And you had to carry your little book around at the end of the course, and the professor signed it. I guess all it really meant was that you'd appeared sometime. And so I took a certain number of courses just to take them. I took Professor Paxu's course in enzymes, which didn't do me much good for modern enzymes, I'm afraid. But on the last day of the class, the students got together and decided we would create some poetry to memorialize the event, and everybody was supposed to come up with a poem, which we put on the blackboard ahead of Professor Paxu's arrival. He was quite touched by this, I think. Attention. I can remember one or two of them. I forget who made this one, but it ran, trypsin, pepsin, and erypsin are found in your intestine. Not a very elegant one, really. The one I had was much more classical, and Professor Paxu, I think, was particularly impressed with it. Maybe I can do it. Conniving thou at man's elation, by enabling fermentation, dear phosphatase by Bacchus blessed, thou esterase whom we love best, think without thee there could be no convivial jollity. Another one, I forget who did this one, was the sly amino acylases love to lurk in funny places. Thus the enzyme histozyme in the liver bides its time.
Well, if they just signed your book, then you had to take an exam on this as
No, the PhD was really based on 3 examinations. Well, the first one was called the quota exam. Now, the total Princeton graduate student body had been limited, I think it was to 300, of which chemistry was assigned 25. But Taylor figured out a sharp deal where he didn't put people on this quota until at the end of their first year, when they had passed an examination called the quota examination. The dean of the graduate school discovered this and canceled it the year after I had to go through this. So that came at the end of the first year, I guess. Then you took a general examination in chemistry a year or so later, and then another one in your particular area of physical chemistry in my case. And so, and then you have to produce a thesis. So the theory was if you had passed these examinations, one didn't worry how you got there. The courses were offered more or less as a service to help you prepare.
Well, did you work closely with Turkevich since he was working on chromium also?
Well, I wasn't working on chromium. Oh, well, he was, sorry, you're quite right. He was, let's see, I think that was really a year after I'd gone. He was working on dehydrocyclization on chromium. So in my particular research work, I just worked by myself. I didn't work with anyone.
How would you describe him as a graduate student?
John?
Yes.
Well, he was, of course, very impressive, very voluble. And when I saw Professor Menges, and when I saw quite a lot of personally, he was an inorganic chemist. After John's oral, I asked him, how did Turkevich do? Very well. He rode off in all directions. So he was impressive.
What was the thing that you remember most about Princeton?
Oh dear. No, that question can't be answered. I have to reject that one. I can remember a number of things, but do I remember one most? No.
Was there a particularly frustrating time in graduate school?
Yes. Since Eyring's course in quantum mechanics wasn't to be given at the time I might have wanted to start it, given alternate years, I signed up for one in physics, Robertson. And I spent a month diligently listening to the lectures, taking notes, trying to understand it. But it was given with the assumption you knew a great deal more than I knew. And so I finally had to abandon it.
Now, as a graduate student, did you attend scientific meetings, or was this left to the professors?
You mean away from Princeton?
Yes.
The only one I think I went to was an ACS meeting in New York. People traveled much less in those days.
What do you remember most about your times with Hugh Taylor?
Well, you see, I didn't really have much in the way of times with Hugh Taylor. He was, as I say, if he was in town, he would almost always come by. That might be 3 minutes. And so that I didn't really have much in the way of time with Hugh Taylor.
Did he leave someone in charge that you could go to, or were you left
No.
totally on your own?
No, you were on your own, but he was there. He was there for 3 minutes a day to look at your graph and suggest what ought to be done next, or he didn't like this, and so on. Why don't you try this? So there was enough direction to keep one going, but not so much as to be tedious. Although it is true that there was a theory among the graduate students who worked with him that the thing you must avoid at all costs was letting him get too near the apparatus. There was a theory he would like to turn a stopcock or two, and there was also a general belief in the graduate students that that would lead to disaster.
How did you get your first teaching job?
Well, after I finished my PhD, they had a fellowship at Princeton, the Proctor Fellowship, several of them, which were good for a year, which in terms of those days paid quite handsomely. And you were a free agent, so I was awarded that. And there was a question, this was now right in the middle of the worst of the Depression. And there was a question as to whether I would decide to go to industry or not. I interviewed some industrial people. I can remember that the year I was interviewing, that Princeton had 4 visitors. You contrast with the present system. Monsanto, DuPont, Eastman Kodak, and I forget the 4th. And Exxon was one. Maybe that was the 4th. And I was offered a job at Exxon. I'm sorry, let's recant that. I was offered a job at DuPont. But just about this time, I got an offer of a job at Trinity College. And Professor Kriebel there, Vernon K. Kriebel, had inquired at Princeton. They'd recommended me. And I was their second choice. First choice was a chap from Columbia, but he was married. And the president at Trinity thought that instructors were paid too little money for them to be properly married. So being unmarried, I got the job.
Did you teach any while you were a graduate student at Princeton?
No, not really. When I was a postdoc, I deliberately applied to have a freshman quiz section, which I had.
This was when you helped the proctor.
But I was not ever a teaching assistant.
Now, what did you do the year you were on postdoc?
Well, I decided to, it got me somewhat started in what I have later done. Because of my contact with Wallace, I'd worked for Wallace one summer. Wallace was interested in whether you could have optical activity arising by the difference between hydrogen and deuterium. So he got me to prepare an optically active compound that was optically active only by virtue between hydrogen and deuterium.
How did you measure optical activity then?
With a polarimeter. And the trouble with this was it really had a very slight rotation. I was never sure it had any. But Wallace got sent it around to several other laboratories, including Whitmore, and it was finally decided it had a barely measurable optical activity. A hundredth of a degree or something. But this got me sort of interested in optical activity, and I began when I thought, well, now, Wallace was interested, and he talked to me about this, in converting cholesterol into its enantiomer epicholesterol. That was involved in inversion at the OH group. And I said, oh, that should be easy. We pass it over a dehydrogenation catalyst, which will make a little of the ketone, and then when the ketone is hydrogenated, you would get the equilibrium mixture. And so Wallace said, well, why don't you try it? And I said, well, I'd want to try a preliminary experiment, I think on simpler case, say like secondary butyl alcohol. He said, I have some, I'll give it to you. So I set up an apparatus and looked at the racemization of secondary butyl alcohol, and then went on to try the cholesterol. And that was a complete failure. There was working with Professor Wallace, a man from EMERC in Darmstadt named Fernholz, and I would give my product to Fernholz and he would tell me if there was any epicholesterol in it. Well, later the problem appears that the equilibrium constant is very heavily in favor of cholesterol, so this should work nicely in converting epicholesterol to cholesterol, in which there was no interest, but it was very poor the other way. And when I went to Trinity, I continued to look at secondary butyl alcohol and its racemization and behavior.
Now, how many people were teaching at Trinity at that time?
Well, there was Professor Kriebel, who, when I arrived, who was chairman of the department. Sterling B. Smith, was next. And then there were two. Trinity just had a new chemistry building built. That was why there was a job. And they had particularly decided that they would have some young instructors they would only keep 3 years maximum, and but they would have a lighter than usual teaching load so they could do a certain amount of research. And the other man in my situation was an organic chemist named E.R. Atkinson, who was later at the University of New Hampshire and then for many years at Arthur D. Little in Boston.
And how did you enjoy that 3 years?
Oh, I liked Trinity. Professor Kriebel and I got along very well with him. I liked him, and I think he liked me. He was very nice to me. And so it was my first independent job, really, in a sense, or at least the Proctor fellow had been independent. I mean, this was now really having to do something. And so I enjoyed it. I had made friends in Hartford, found a wife even, and so I enjoyed that period.
And you continued working on optical activity all the time there? Or?
I continued to look in the reaction of hydrogenation and, I should say, the racemization of secondary butyl alcohol, a system I abandoned then after I left Trinity.
And this racemization that you did was hydrogenation, dehydrogenation, not loss of the OH.
Well, no, my theory originally was that I was just going to get a little ketone and then rehydrogenate. But it turns out that when I analyzed it, that the racemization was faster than could be explained by that. That must be giving some racemization, but there was a racemization process that gave a lot faster racemization than that. And that was something of a puzzle. I mean, let us say organic mechanisms had just barely started then. I'd heard something about it, and that was one of the things I was interested in applying to heterogeneous catalysis. Taylor told me he thought this was useless, but I went ahead and tried it anyway. Probably Taylor was right. And so how does one get racemization of secondary butyl alcohol? Now, if you just cleave one bond and then reform it, that doesn't give you racemization. If it's one simple process, you'll just get back what you started with. So I thought I had to take off two groups. So I even made a proposal, which might seem ludicrous today, that the alcohol was really in essence dehydrated. That is, taking off H and OH, which now made what would be called a carbene. And then it was rehydrated, and now that could go from either way, perhaps. So that was the only idea I could produce at the moment, and I still don't really know how it goes. I have suggested later that it might involve rollover in an absorbed ketone.
Well, how did you come to Northwestern then?
Well, it so happened that, well, I should say a word. The Trinity College had a new laboratory when I arrived. It's a very handsome laboratory. They just celebrated their 50th anniversary a couple of years ago, and they asked me back to give a talk after dinner on the old days. I think I was the only person they could locate that was still alive, who'd been there when it opened. And who gave the money was a deep secret. I never learned while I was there. He'd sworn everybody to secrecy. So Northwestern was to get a new laboratory, and they were going to need more people because this laboratory at Northwestern arose in the following way. Northwestern at that point had a small engineering unit that did only electrical engineering. There'd been a faculty committee who'd surveyed it, and they gave a report that the thing should be either abolished, Northwestern should get out of engineering, or they should build a real engineering school. And shortly after that, the university received a letter from some lawyer, I believe, asking if Northwestern had any interest in engineering education. And so the president could take out this report, modify it slightly, and send it off. Apparently a number of universities treated this as probably a thing of no consequence, maybe of some crazy character. So Northwestern was accepted. And it turned out that the man who was going to give the money had a passion for anonymity. And the Board of Trustees had to agree to keep absolutely quiet about it. So the building was in terminal stages of planning when one of the members of the Board of Trustees leaked. They got into the newspaper that a certain Walter P. Murphy was going to give the money. Well, Mr. Murphy was incensed. How could you trust the university to run an engineering school when they couldn't even keep a simple secret? So he canceled the whole thing. But after a couple of years, he came back and he said, well, he would give Northwestern one more chance. And this time, apparently, they must have behaved satisfactorily because there was built the engineering school here. And Murphy gave them several $1 million to handle the period while there weren't any students and building up students. And the building was now going up, and one of the things that was told Mr. Murphy was that, well, you see, we will have to give chemistry and physics courses to the engineers, and both engineers and physicists are in one small building on the south end of the campus, which is already hopelessly overcrowded. They couldn't take another student. And Mr. Murphy said, well, that won't be any problem. Just build the physics and the chemistry laboratories into the Technological Institute building. So that was done, but now they needed some more people, and Professor Hines was going around the country looking at laboratories, new laboratories, getting ideas, and naturally he went to Trinity, which was at that point a very deluxe laboratory. It still is, really. Because I'm sure Professor Kriebel is a good Pennsylvania Dutchman, went out asking for twice as much money as he thought he could get, and he got most of it. I taxed him with this once later, and he just laughed, but he didn't deny. However, Professor Hines, this was in the summer, Professor Hines came in, found me in the laboratory, and offered me a job.
And so you moved to Northwestern in what year?
1930, fall of 1939.
And how did you find the transition? Was it a big change?
Well, this was my first visit to the Middle West. Maybe I expected to see cowboys and Indians. But Evanston, of course, is a rather tame part of the West. And so I don't know that I thought it particularly drastically different. At that point, of course, I'd been teaching in a small college, so there was no comparing Northwestern with Trinity College. As far as comparing with Princeton was concerned, at that point, Northwestern didn't look anywhere near as handsome as Princeton did. A situation that's changed dramatically over the years.
How big was the student body in '39?
I haven't now the faintest memory, but no, if I committed the problem is, you asked the student body, but we've got a College of Arts and Sciences, the School of Music, College of Education, School of Journalism, School of Speech, Graduate School, and I don't really know how many it was. It was probably half the size of what it is now.
Oh, was it Murphy that gave the chemistry lab to?
Murphy gave the chemistry laboratory. So I have spent my entire scientific life in laboratories built by Walter P. Murphy. He was a man, I think he'd never been to college, if my memory is correct. He made money in railroad equipment business, and he was a bachelor. And he gave the money for the building here, and then when he died, he left the residue. He made certain specific gifts, and then left the rest of his estate to endow the Technological Institute building.
And what did you start working on when you came to Northwestern?
Well, when I arrived at Northwestern, the new building, of course, was half finished. And the old building, as I indicated, was terribly crowded. But there was in the basement of University Hall one fairly substantial room which was occupied by the Apoteyev laboratory. Apoteyev came to the United States, I think it was 1932, and at that point you had no easy job getting into the United States because of the Depression and employment and so on. So it so happened that Apoteyev had left Russia. He'd gone to a meeting in Berlin. They let his wife go with him, and he neglected to return. And he was there for 2 years, I think. And one of the directors of research at the Universal Oil Products Company, Gustav B. Ugloff, ran into him there and offered him a job at UOP, which he accepted. But the problem was getting him into the country. Well, Egloff went to Ward B. Evans, with whom he had been a graduate student at Columbia. And Evans arranged to have Apoteyev appointed a lecturer at Northwestern. Well, now, the government was concerned about unemployment among industrial chemists, but nobody worried about college professors. So that's how Apoteyev got in. He was a lecturer, but he couldn't lecture very well because he hardly spoke English. He never learned to speak English very well, really. But after a little bit at UOP, he decided that he wanted to be able to do certain kinds of academic research not appropriate in an industrial organization. So he got UOP to set up a laboratory here. And there was some room in there, and Professor Hines said, well, now, you know, we just don't have a single place we can put you. Why don't you go in and work with Apoteyev for a while until we can get a building room for you? So I did. And I worked with Apoteyev. We published a paper from some of the work I did. But it wasn't entirely satisfactory. I mean, I was supposed to be doing my own research at this point, and then I found another place where maybe I would have a little space over in another building where chemistry had a little corner. So I moved to there.
And how did you find working with Apoteyev?
Oh, working with Apoteyev was fine. He came to Northwestern one day a week. And he was very old school for a gentleman. And it was quite pleasant work with him. He always looked upon me later as one of his boys. We have a system, started a system where we meet for lunch on Tuesdays. Everybody brings a brown bag, and each faculty member in turn gives a talk. And so when I gave mine, Apoteyev would always come.
How did he work in the lab at that time?
Well, of course, he was only here one day. Primarily, he was director of research at the Universal Oil Products Company. One of his students at this point, working here, was the same room I was Vladimir Hensel. And Apoteyev called up Hensel daily. And I told Hensel, listening to him, he very clearly was a da man, because Apoteyev would be on the phone, Hensel would answer him, and most of the conversation would be da, 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 occasionally ochin harasho, but mostly da. But now, he didn't usually talk with me on the phone. It was much easier at that point to talk to a Burt Davis in Russian, which Hensel obviously could do and Herman Pines could do, but I couldn't do.
But if he came to your lectures, he must have understood English.
Oh yes, over the years he was learning English, and he could speak English some. He had had some kind of a throat ailment which left him with a very husky voice. It was hard to understand at best. And so he, particularly in a scientific context, he could understand English.
Well, what was the things that he was working on at that time that UOP wasn't interested in?
Well, what I was looked at was the making of mixed ethers by a catalytic process over a phosphoric acid silica catalyst. And then I'd started off doing some work on it, would have been very fashionable later, decomposition of methanol over certain catalysts making hydrocarbons. But I never finished that because an opportunity came up for me to get my own space, and I went into that.
How would you describe Petyev as a person?
Well, he was a good-looking man, well-built, not thin but not fat, and he was very formal in his ways, as one would, I think, expect with his background, but very pleasant. Always. And the remarkable thing about Petyev that I found profitable studying him was I thought, okay, now here's a man who's done a number of important things. More than could be ascribed just to luck. He may do one or two things by luck, but he's done too many. And Petyev was an organic chemist. And as near as I could see, the way he operated, he would get a certain idea. But his knowledge of organic chemistry was so extreme that he would now just run through a computer search of possibly related reactions. And he could say, oh no, this won't do because here's this possible side reaction, and so it did, and so on. So that I think he worked by a series of analogy with a very extensive knowledge. Whenever I hear people, or I would sometimes hear students say, why should I have to learn all that crazy organic stuff? I can always look it up. But you can't look this up. You have to have it in your computer storage and some kind of a linkage so that it comes into your mind when you start to work on it. And that Petyev had remarkably.
So he looked at himself more as an organic chemist?
Oh, he was an organic. He was an organic chemist, and all the reactions he did. That's not quite true, but mostly the reactions he did were organic, and his way of thinking, in my judgment, was organic. And the important things he did were primarily applications of, or at least among the most important things he did were applications of organic chemistry to heterogeneous catalysis, or vice versa.
Now, did he think of himself as a catalyst person, or?
Oh yes, he was definitely a catalyst person. But just for example, there were other people who were catalyticers, but were primarily organic chemists. Suddenly I can't think of it. Who was the man at the University of Wisconsin?
Atkins?
Homer Atkins. He was certainly an organic chemist who did heterogeneous catalysis.
Did you continue to interact with Petyev after that, or?
Well, as long as Petyev continued to come to Northwestern, he was in the laboratory pouring one thing from one test tube to another within 2 weeks of his death. So, as I say, I think he looked upon me as one of his boys. So, I mean, we always had a pleasant hello, but not too much. conversation extensively.
Who were faculty members when you came to Northwestern?
Well, I ran into two of them who had been at Princeton with me, Selwood and Arthur Frost. And there was the other physical chemists besides Selwood were Malcolm Dole and Frank Gooker. Gooker later left to go to the University of Indiana, where he was finally dean of the College of Arts and Sciences. Malcolm Dole retired at 65 and went to Baylor, where he retired again, I think, at 79, and still seems to be in very good shape. Among the organic, Professor Murray Hines, who was the chairman, was an analytical chemist, and in addition to his Professor Merrill Suter, organic chemist, our leading organic chemist probably was Professor Charles D. Hurd, who is still at Northwestern and retired status, remarkable condition for a man of over 90. Comes to our seminars regularly and asks questions. And there were some younger ones, ones who were here when I arrived. There were a number who came because of expansion. Several who came just after I arrived in the next year. Well, those are the ones that are coming into my mind rapidly.
How would you describe the young Selwood?
Well, Selwood, of course, was always a very thorough, careful worker. And he tended to concentrate. All of his work involved a magnet. And Selwood had a good general knowledge of chemistry. He had good experimental ideas. He was never a hail fellow, well met type. But I saw a great deal of him. There were 4 of us who started to have lunch together. And I will now begin to remember more faculty members, because now that immediately makes me think of Robert K. Somerville, who was an organic chemist working largely at dioxane derivatives. And Selwood, Somerville, and myself, and Robert H. Baker, who arrived the year after I did, started having lunch together. When the Technological Institute building was open, there was no place to eat lunch near it. Before that, I'd usually gone with several of the faculty members, often Selwood and Somerville in particular, down to the North Shore Hotel cafeteria for lunch. So we started to bring a paper bag, and that's still a quite common custom in the chemistry department. So we started to meet in Selwood's office for lunch. And another group later started the same thing, but then decided, why didn't we all move to the conference room? And there we still are. So that I saw Selwood frequently in the building, and also we saw them socially quite a lot.
Well, I just learned that he was working on the element at that time that was called selenium as a graduate student. Did he ever express frustration over that? Or?
I don't think so. I've already mentioned that he did his PhD in rare earths at the University of Illinois with the alleged discovery of selenium, or the discoverer of the alleged selenium, whichever way I should put it. But what he did as a graduate student didn't seem to me to have had much influence on what he did later.
How did he come to start working in magnetism? Was that
I don't know. I don't know. He may have been involved in his rare earths, for all I know. But his first thing was he got a magnet given by some funds he managed to get out of the National Research Council. And he always was very insistent. That was his magnet, not Northwestern's.
Well, did you work with him on Chromia over the years, or was?
Well, I didn't work with him. We did. For example, in one case, he gave me a nice set of nickel silica catalyst, which he'd characterized magnetically, which I used for catalytic reaction. But his work, he was quite concentrated in his work. It wasn't immediately going to fit into anything else.
How did he interact with graduate students?
Well, Pierce was a very reserved person. He wasn't at all ebullient or effusive or hail fellow well met. But I believe that the graduate students he had thought well of him. I mean, we had some famous ones like Bob Ishans and so on. And but he was primarily, remember, he was originally a Canadian. They may have had some influence on him, but he was rather reserved. Unless you got to know him quite well.
Who was your first graduate student?
My first graduate student I'd gotten before the war. I got in the war. I went in the Navy at a certain point. And we ended up, both of us, at the Naval Research Laboratory in Washington. Harry Cole, there, worked for his career in DuPont. I had thought that following up the work I had done at Trinity, that we could measure the equilibrium constant between acetone, hydrogen, and isopropyl alcohol by direct equilibration. So we set up an apparatus in which we used a copper catalyst and passed the alcohol or the ketone and hydrogen, or in the terminal stages a mixture which I thought was close to equilibrium anyway, and we measured the equilibrium constant by that method directly, and we also did secondary butyl alcohol. And I still see occasional references to that. Apparently they turned out to be more or less right. At least I'm not aware of anybody arguing they're drastically wrong.
How did you come to go to the Naval Research Lab?
Well, when I was in college, I thought I was a pacifist. But then when Mussolini invaded Ethiopia, it suddenly occurred to me that I wasn't a pacifist. So having stopped being a pacifist, I applied for a commission in the Navy. And coming from Annapolis, I had certain contacts which may have helped. And I got myself a commission in the ordnance. And when the war came, nobody called me up. I would try to find out what was going on. They would say, well, right now we haven't any definite need for you, and maybe you better do what you're doing. But finally, there was an edict that went out that everybody on the reserve who hadn't called up was to be immediately called up. So in October '42, I went first. They sent me to what was called indoctrination school. That was at Fort Totten in New York. And then I was sent to an ordnance school in Washington in the Naval Gun Factory. And then I was sent to an ordnance laboratory the Navy had in Silver Spring, which I didn't find at all agreeable. The commanding officer I thought was a nitwit. And I applied to be transferred to the Naval Research Laboratory. Now, that was theory forbidden, because that was under the Bureau of Ships, not under the Bureau of Ordnance. But somehow it went through, and so I was there for a couple of years, working in corrosion.
How did your independent personality fit into the military? Is that any problem?
Well, I'd grown up in Annapolis. I knew what to do. And I tried to do it. I don't think I had any problems.
Did you run into Brunauer in the Navy? He worked in the ordnance? Or?
No, I never ran into him in the Navy. I never saw much of him go. But he lived in Evanston for some years when he was the Portland Cement Association, so I used to see him occasionally then.
How would you describe him?
I really didn't know Brunauer that well.
What did you do in the Navy on corrosion? Was it surface science? Or?
Oh, that was before the day of surface science, good heavens. The Navy had two things they get corroded. The first thing is people don't ordinarily think of is aluminum. But we had a testing station down in Curie Beach, North Carolina, and you take an aluminum 16th-inch sheet and stick it in the ocean and haul it out 6 months later, and it's got holes in it. Chloride iron is a very bad promoter of corrosion, of course, of both iron and aluminum. So I did most of my work on corrosion of aluminum. And one of the standard methods of protecting a aluminum against corrosion was to anodize it, and then in particular paint it with the zinc chromate primer, because chromate also inhibits corrosion of aluminum. And so I studied the properties of anodic films, and I got ways of removing them from alumina, studying their diffusion characteristics, force structure, and things like that. I even measured the surface area of some anodic film by the chemisorption of a gas. Now my problem was which one should I use that was available. It wasn't. At this point, nitrogen would have posed me a little problem because you needed liquid nitrogen. The laboratory there had liquid air. So I looked, furthermore, it's hard to get enough of an anodic film so you could use liquid nitrogen. I mean, its area isn't big enough. So I thought that one should use a gas which had a much lower, a gas at a temperature so that its vapor pressure was very much smaller and the correction for dead space was negligible. And so I looked through the list and thinking in terms of something I could use liquid oxygen for as the reference temperature, and I ended up on ethylene. And it seemed to work all right, but of course I made a mistake. I should have invented krypton. Because as far as I know, I'm the only person that ever used ethylene. It works. As far as I know, it works as well as krypton, but krypton sounds much better.
Did you write this up?
Yes, that was published.
And how long did you stay in the Navy?
I was in the Navy from October 42 until January 46.
And what was your impression of this period?
Well, there it was. I don't know that one tries to get an impression of something like that. At the Naval Research Laboratory, I was doing work that I thought could be useful and at the same time was interesting. So I was reasonably happy about that. From a child, I knew the Navy, so I really didn't have any problem with the Navy. And we lived in Alexandria. I mean, of course, my family lived in Annapolis, and I would try to save up enough gasoline so I could drive over to Annapolis periodically. It wasn't near the area where I'd grown up, so I knew the area, so that it wasn't too bad.
What happened to your teaching duties while you were in the Navy?
Well, I was at Northwestern. I mean, all the colleges at this point had lost most of their male students. The northwestern part of the laboratories were taken over by part of the government worrying about gas masks. And so that I don't think they miss me at all. Probably glad not to have to pay me a salary.
Did you teach any while you were in the Navy? Or?
No. The thing I did that way was the other way around. For a while I was taking an afternoon course in Russian, which I never followed up.
Did you get on any ships?
Oh, it was called the Battle of the Potomac. I was never on a ship of any size whatsoever. I rode on a boat every day because I lived in Alexandria. In Alexandria, there was a Navy torpedo station, and the Navy ran a boat I can cross the Potomac for the benefit of people who lived in Alexandria and worked in the Naval Research Laboratory, which is right on the Potomac, a little bit upstream from the station. So every morning and every afternoon, I had a nice ride across the Potomac, which was, in 90% of the weather, a rather pleasant way to commute. It's by far the best method of commuting, I'm sure.
Did you encounter any other scientists in this work that you'd like to mention, or that worked in surface area science, or in...
Well, I knew Zisman a little. Zisman was head of the surface section. I was in corrosion. And he was a well-known man. I knew him some. And of the people scientifically that I had contact with, I would put him at the top. I also had quite a lot of contact with a fellow named George Gordon, who had gotten a bachelor's degree at Princeton in chemistry and started off to do graduate work, but then been interrupted by the war. And he came out to Northwestern at the end of the war and did a PhD with me. And he and his wife have been very close friends of ours.
And then you came back to Northwestern in '46 and started again?
Came back in '46 and went back to work.
And was there a difficult adjustment, or?
Oh yes, you had to find a place to live. And that was very difficult in Evanston at that point. I don't fully understand why. Evanston is the same size now as then, and it's by no means so difficult today, but right then the demand on housing in Evanston was tremendous. The Northwestern even just started at this time a substantial apartment house for faculty, which was later abandoned for that purpose. It was shifted to the girls' dormitory. There just being very little demand for it. But by great good luck, a chap I knew who'd been at Northwestern, who we connected with one of the government projects, went to the University of Wisconsin, and we were able to inherit the house he was renting. And so then the house rent was quite cheap. And I spent my time for a while trying desperately to save enough money to make a down payment on the house. And generally to find that the rate at which I was building up my savings was about equal to the rate of inflation on prices of houses.
So then you splurged and bought one without saving for it, or?
Oh no, I do have to make a certain down payment after all. But I wanted a house that was near enough to the university to be walkable. But we've always been a one-car family. We've never owned two cars. And we looked and looked, but finally, in the very late fall of 1952, we found one we wanted to buy, and which the man accepted our offer on, the owner, and so we moved into that house in February of '53. And the house was built in 1924 originally. '53. 88, so we've been in it more than half its life. Looks like it too.
Oh, do you remember your first trip overseas?
Overseas?
Mm-hmm.
Oh, indeed, because I didn't get overseas until I was rather elderly. I've been chairman of the chemistry department from 52 to 57. And in honor of that service, I was given a quarter's leave of absence. And I decided to go to Europe and visit catalytic laboratories. So, I had a grant from the Army Office of Research. And they gave me an order on the military air transport to fly from New Jersey, McGuire Air Force Base is the name of it, I think, near Trenton, to Europe. So I got in this plane, and it went to an air base, Air Force base in Nova Scotia, landed. This was equivalent of a DC-6 airplane. And then we went from there to Glasgow, where they took us ashore and gave us breakfast, and then they landed us in Paris. And then they put us in a bus, which made a tour of the Paris railroad stations. So my first visit was to go and see Téchener and Trombouz in Lyon. So they dropped me at the Gare de Lyon. And now that was the first time I've been in Europe. Except that in the flight from Glasgow to Paris, it was overcast. But at one moment, we went through a little hole in the clouds and could see the ground. And there I saw a jewel of a castle surrounded by a moat. And it closed again. So I thought I had a good introduction to the continent. Now I got into the railroad station, and now my problem was to find out, could I speak French? I'd taken 2 years of French in high school, and when I got to college, in theory, I should have taken the second college year of grammar. But that looked a bit tedious, and I persuaded the professor to let me take the literature course instead, which I think was lucky, because although my grammar has always been a bit weak, this greatly expanded my vocabulary over what it would have been if I had taken the grammar course. And then towards the end of the war, after the U.S. had starting to go into Germany, the Army had an arrangement where they were going to send a bunch of scientists following the troops who would interview and see what the Germans had been doing. And this upset the Navy, who thought they should do it too. So I was appointed as one of the Navy personnel who were going to do the same thing. I'd even gone so far as to go up to the State Department, where they took my picture, substituting a very loud checkered tie for my black tie and my uniform. This would be a civilian passport. And so I thought, well, now I better work on language. And I had some German in college. I could read scientific German, no trouble, but I didn't have much outside of that. And I thought my French was closer to useful. So I worked rather hard on French for a while. But then it turned out that it was decided that only the Army would do this, so I never did it. But I had worked some on French, and then I kept up occasion trying to read French and so on, but now could I speak it? So I got in the Gare de Lyon, and I found I could get lunch all right, which greatly pleased me, but then I got on the train to Lyon, and it would be dinner on the train ride, and so I didn't understand the system that you had to have a reservation for dinner on the train. But I had been talking some to people in my compartment, and they told me now the man will come through the train ringing a bell, and he will tell him you want dinner. So he comes through, but sorry, all reservations have been made. And And they said, don't worry, go and stand at the head of the line. Somebody won't show up. You'll get in. And so it happened. And I was now at a table with 3 businessmen returning from a day in Paris to Lyon. Well, I tried to say a few words to them, but they couldn't understand anything I said. And I was sort of crestfallen, and I said, Je regrette que je parle ainsi épouvantable français. I regret I speak such terrible French. They understood that. Now they were French, so they were obligated, being French, to say, but no, it's excellent. And having said my French was excellent, they were obligated to understand me, which they now could do. So that was my introduction to Europe. I remember that well enough.
And who did you meet in France? Tishner? Or?
Well, I went to Lyon. I was going to visit Tishner and Trombouz. And there was also a man from Rome-Poulenc who had been at Northwestern with Herman Pines for a while. I looked him up, and I discovered for the first time that amazing phenomenon called dinner in France. A man from Rome-Poulenc took me to a restaurant on the outskirts of Lyon in an old modified villa with a beautiful view looking out, and a wonderful dinner inside. That was my first real French meal, and I was much impressed. And then the next night, there, Trombouz and Tishner are going to take me out to dinner, and we pull up in front of the same place. And I go in, and Madame at the entrance, I can see, has recognized me as going to say something, but I fix her with my steely glance. She keeps quiet. I wasn't anxious to. They were going way out of the ordinary to take me to this restaurant. I didn't want to let them know I'd been there last night. And so they were the 2 people. I met other people there, like Professor Prater, but they were the people I went to see.
This wasn't too long after the war. What was the status of the lab?
This was 58.
No. Oh, okay. I thought you...
Well, at this point, they were still at the chemistry laboratory of the university. And I have a picture of them, which I took with a street sign showing that we are at the intersection of the Rue Victor Grignard and another famous French chemist in the other way. Which one? Gone at the moment. And that laboratories were still pretty old-fashioned then. Of course, now, not long after that, they moved to the Institut de Recherche sur la Catalyse in Villeurbanne outside of Lyon.
And did you visit any other labs on that trip?
Oh, I visited lots of them. I went from Lyon. I paid a non-scientific visit to a cousin who was at Villefranche-sur-Mer near Nice. Then I went to Italy. I was combining this with a little tourism too. I went to Italy and I visited Bologna. But I went to stop at Florence for a few days. And I visited, among others, Professor Schwab in Munich. I visited Professor Schroet, or then of course Dr. Schroet, because it's in Amsterdam, the laboratory there. I visited Nancy, and I visited Göttingen. I had an acquaintance with Manfred Eigen, who still hadn't got a Nobel Prize or anything like that, and I visited him for a day. And then in England, I visited several people: Stone, Goldfast, Sid Campbell, Bond, I think I visited the main European catalytic laboratories at the time. That was what my schedule was based on.
How would you describe Schwab?
Professor Schwab? Oh, well, I arrived, I'd been in Amsterdam. I took an overnight train to Munich, and I was arriving on the 1st of May. And Professor Schwab suspected, and he was completely right, that I didn't understand the 1st of May. A major holiday in which everything stops. All he knew was I was arriving in the morning. He didn't know what train. And he was down at the railroad station checking all the arriving trains from the north until he found me. And then he took me off to Upper Bavaria for the day. A most memorable day. It was a beautiful day. And I saw some of the really famous sites like the church at Wies, Ettal. I watched a maypole being put up in a little town. I think it was Rotenburg or something like that. And that was a wonderful day. Professor Schwab has always been very hospitable. In fact, even once when my daughter was spending a summer in Germany in a Goethe Institute, they asked her down to Munich for a couple of weeks, because they have a daughter about her age.
Had he gotten his lab started again and going strong by this time after the war, or?
Oh yes. I remember that I was going to visit his laboratory, and I got by mistake into the new, it was just still being finished, inorganic laboratory. And there in the hall I ran into E.O. Fisher, whom I'd met visiting Northwestern. And he took me to Schwab's laboratory. We had to go between a building working over two rather narrow planks, I can remember. Do you think we might have it?
Well, we had gotten to Professor Schwab in Germany on your European tour.
Over the years, I've seen him fairly frequently. He's visited us here several times.
Well, on this trip, did you spend more time in art museums or in catalyst labs?
A judicious mixture of both.
When did you first become interested in art?
Well, that's an interesting question. And not so easy to answer. But probably when I was in graduate school.
And
By no particular reason. It was very gradual growth of interest.
and so you developed and learned it as a sideline, I see.
Well, it has to be a sideline. I can't afford to have it a full line.
Do you paint, or do you just...
Nope, I just look and collect a little.
What was your next trip abroad then?
The next year I went to a meeting of the All-Union Congress on Catalysis in Moscow.
That was in 1959?
59, I think.
And what was your impression of Russia then?
Well, when I left, I got on the SAS plane, and it was snowing. This was in about late November. And they had to de-ice it by hand. They weren't satisfied, so we all had to get off, and they did it again. And finally we left. And the moment the plane was really pulled away from the hangar, stewardesses went through the plane distributing foreign newspapers. And so I was glad I went, and I was glad I left.
Did you ever go back again?
I was there this summer.
And have there been significant changes? Or?
Well, it seemed to me things were obviously distinctly more prosperous, not prosperous really, but less unprosperous. Now people have enough money occasionally to buy a Coca-Cola, which are rather expensive, but you see them all over the Soviet Union.
Was there a apparent difference in the Russian people, or
Oh,
too short a time to
too
tell?
short a time to tell that. Though I must say, on the last trip, where I went to Novosibirsk to a memorial meeting for Boreskov, and they certainly were people were very, excuse me, pleasant and hospitable. No doubt of that.
When did you become chairman of the chemistry department here at Northwestern?
1952.
And was that something, an honor given to you, or were you interested in trying administration?
No. You know how you become chairman. You say, well, I really don't think I want to do it. And then they say, oh, but if you don't, so-and-so will. And so you do it. I was chairman for 5 years. And I can't honestly say I was glad I did it, in some ways. But I can honestly say I was glad when I wasn't doing it.
And did that interfere greatly with research?
I tried to figure that out at the time. I think that I paid as much attention to graduate students as I had. What badly suffered was my general reading. I had to make a determined effort to catch up on that.
And what was the hardest part about being a department chairman?
Listening to each faculty member with his own particular gripes.
And how do you handle that?
Judiciously. The best you can do is to try to make all people equally unhappy, then you've been fair.
How did you get started on your deuterium tracer studies?
Well, when I was a graduate student, right next to me people were studying it, like Morikawa. In fact, Taylor had a big push on deuterium isotopes, and I rather reacted against it at the time. But then, when I came to Northwestern, I say I worked with the Patya, but then when I got my own little space, little corner, it simply wasn't possible for me to continue in heterogeneous catalysis. So I started in reactions of optically active secondary butyl alcohol in a more really organic sense, like reacting secondary butyl alcohol with sulfuric acid to make the secondary butyl alkyl sulfate, and studying reactions into what could racemize secondary butyl alcohol. I did some work with anhydrous hydrogen fluoride. And I got interested in the reactions of secondary butyl alkyl sulfate, in general alkyl sulfates, but the optically active study told you some things. These were compounds which had been widely studied back about 1860 as alkylating agents before halides came in, like secondary butyl bromide, in the present case, or iodide. And I continued to work on them for a while. When we moved in this building, I started back into heterogeneous catalysis, but only partly, and it wasn't until the end of the 50s that I began to devote myself exclusively to heterogeneous catalysis.
And what was the work that led up to the flip-flop mechanism?
Well, what I started off with in the 50s, early 50s, was a study of optically active secondary, what should I call it, methyl ethyl propylmethane, to make it clear that it's optically active. So I did some look at at that. And then that obviously was going to require some isotopic tracer work to try to elaborate this. At that point, we didn't have a mass spectrometer, so I had to send it down to the Illinois Institute of Technology. Since that cost me money, I had to make sure I sent only the good samples. We were determining the extent of deuterium exchange first by infrared spectroscopy, looking at the CD band, and then choosing the ones to send for examination. And later, Northwestern got a mass spectrometer which we could use. And this turned out to give some rather interesting results. At the same time, Campbell was studying exchange of hydrocarbons, doing very similar things to us, but he was working mostly, or I think exclusively, on evaporated metal films. So I primarily stayed on supported catalysts, so we did look at one case at reaction on rhodium films. And the problem really arose. Campbell had discovered that if you exchanged cyclopentane with deuterium, you got a maximum at D5, then D6 was small, and then it rose to D10. And the question was, what was the origin of this? And we had originally tried cyclopentane, but we were at a rather high temperature where that maximum at D5 disappears. So we, in the course of this, went to lower temperatures, palladium, started off on nickel. And the key to this happened when we ran methylcyclopentane. And there was a maximum at 4, a maximum at 8, and a maximum at 12. And I was out walking my dog one evening before I was going to bed, and the solution suddenly popped into my mind. I didn't know I was thinking about it, of course, the usual way. That you could exchange only hydrogens which were in eclipse conformations, and that to get over on the other side of the ring then, you had to have some additional process which permitted you to get over. Now with methylcyclopentane, if you initially absorbed on the side of the ring with the methyl group, there were only 4 hydrogens you could exchange. If you absorbed on the other side, then you could exchange all 5 ring hydrogens and the 3 methyl hydrogens in a series of alpha-beta migrations. And then if there was some way to get to the other side of the ring, then you got 12. The methylcyclopentane showed this very clearly.
Now, was it just by accident that you used methylcyclopentane, or was there forethought?
Well, that's an interesting question, but I don't guess I really remember. My general view had been that, well, most physical chemists in those days, if they wanted to look at exchange of hydrocarbons, would start off on methane and maybe go to ethane and propane. But I started off with optically active 3-methyl hexane. And I'd been somewhat influenced by organic mechanism work here, where with simple compounds you didn't usually learn too much. You needed to have more complicated compounds, and also you needed to study a variety of different compounds. So, having looked at cyclopentane, it seemed logical to see what would happen to the methyl group if you went to methylcyclopentane. But that I anticipated what would happen? No. I didn't do it to test out this idea because I hadn't had the idea yet.
And then what led you to the Burwell Zoo as...
The which?
The Burwell Zoo.
Oh, well, that was fairly straightforward too. If you looked at exchange of alkanes, simple alkanes, you immediately got the notion that you had to have a monoadsorbed species, that is a sigma alkyl, and that if you went to exchange that by more than one hydrogen atom, you would go of necessity into a diadsorbed, alpha-beta diadsorbed species. Later some people preferred to have this bi-complex, it's hard to tell them apart. And when we got to methylcyclopentane, there had to be some thing that led you to get from one side of the ring to the other. We also did some work in hydrogenating dimethylacetylene, methylalene, butadiene, and from the dimethylacetylene you clearly needed a diadsorb species and a monoadsorb vinyl species. And from methylalene you needed to have a slightly different. You had to have a diadsorb vinyl-like species. Butadiene, you needed to have an adsorbed allele. And so this was beginning to be a fairly large number of different hydrocarbon species that would be required. Well, it's rather interesting perhaps that when Polanyi, I don't mean Polanyi, Ariucci and Polanyi, first made the proposal of their mechanism, they had what we could now call a sigma alkyl and a diadsorb species. Some people think it may be a pi complex. Some people still believe diadsorb, and the literature has had a lot of controversy on that, particularly recently in surface chemical physics. But Ariucci and Polanyi, fortunately, weren't well acquainted with inorganic chemists, because the inorganic chemist had a dictum after many unsuccessful attempts that you couldn't make any such species as a sigma alkyl and it's in organometallic chemistry rather. And there were Ariucci and Polanyi assuming that that was an intermediate. If you look at Pauling's Nature of the Chemical Bond, you'll find that Pauling explains why you can't have such species. Unlike, say, cyanide complexes, are nice and strong because they have resonance contributions. But methyl surface, or Pauling's talking about methyl, say platinum or something, that couldn't happen. So that when we were first proposing these different species back in the mid-50s, presumably all the inorganic chemists thought this was impossible. And then Boston discovered ferrocene. Pretty soon there began to be more. For a long time I was keeping a file on these, but finally it was clear that there were so many different organometallic species involving different kinds of carbon bonds that you could have almost anything you wanted if you just wanted an analogy. It was free. And I finally stopped keeping the list. It just became too numerous. So that many of these, certainly one can imagine on the surface, and that creates a zoo.
And what led you to the supported metal complexes?
Well, I had a feeling that I didn't want to get all of my ideas on catalysis from palladium and nickel and platinum. So I had noticed a paper in which it was reported, just one sentence, that chromium would hydrogenate ethylene at quite low temperatures. And so I thought, well, let's look into this. And sure enough, we duplicated the results of the paper. It was a paper by Weller. And then we decided to try isotopic exchange. Well, we all, as I say, we hydrogenated some olefins with deuterium, and it turned out to be quite different from metals. On ethylene, you got a simple dideuteroethane as a product. And these were very active catalysts for this, working well below room temperature. In fact, you can measure the rate of hydrogenation of propylene down to minus 60 or lower. So it was an extraordinarily active catalyst. And the products with ethylene were very simple, just dideuterol. When you got the more complicated olefins, butenes even, for example, you began to see a little more complicated material, but still it was mainly dideuterol. But apparently the higher ones you would get involved in olytic species. And we looked at isotopic exchange with alkanes, and these now turned out to give, with this very simple olefins, methane and ethane, a simple monodeuteral product, whereas metals give you a complicated distribution. So it seemed to be like an interesting case. Well, that was on an oxide. The first time I tried more complicated species rose primarily from some papers by David Wan, who was then at the University of Edinburgh. And he had, well, Banks and Bailey had deposited some molybdenum hexacarbonyl on alumina, and they had given it some kind of an activation, and it was on this catalyst that the olefin metathesis reaction was discovered. They discovered it. And Wan did some work with infrared, and I thought this might be interesting, and I wrote to Kemble and asked if they were planning on looking at XPS. And Kemble said, well, there would shortly be a paper, but he wasn't going to work at that anymore. I wanted to go ahead. So we didn't ever do anything serious with XPS, but I thought I'd do a little chemistry. And I had a graduate student, beginning graduate student, Alan Brenner, who was willing to work in this area. He still does. And so he started off with molybdenum hexacarbonyl, doing something that the group in Edinburgh hadn't done at all, looking at the chemistry. And this turns out, my judgment, to be a good example that if you only do spectroscopy, which the Edinburgh group had done, you can miss some important things. If you take ordinary alumina and heat it to, say, 450 degrees, it'll have about 4 OH groups per nanometer squared, and originally it would have about 15 if it was fully hydroxylated. Now, if molybdenum hexacarbonyl absorbs on this material, but then it reacts, and whereas ordinarily molybdenum hexacarbonyl is quite inert at room temperatures, but here it reacts, liberating carbon monoxide. And we could measure the amount of carbon monoxide, and because of the work with chromia, I knew how to make systems that had very low oxygen content, and we did that. And we discovered several things that hadn't been seen previously. First, molybdenum hexacarbonyl decomposes on alumina, losing carbon monoxide, and goes to a tricarbonyl adsorbed. And that has some stability. But if you heat it above about 150, it loses carbon monoxide, but simultaneously it evolves hydrogen by reacting with the surface OH groups, and the molybdenum becomes oxidized. At about 280 degrees, it was giving a molybdenum oxidation number of about 2. In addition to hydrogen, a little of the hydrogen got diverted to methane, and by adding these up, we could calculate the molybdenum oxidation number. And if you keep on going to higher temperature, more hydrogen comes off, and by the time you get to about 500, you nearly have molybdenum 6+. And this oxidation and this general behavior had been missed. Furthermore, we discovered that if you passed a pulse of oxygen over one of these catalysts that was about molybdenum 2, that you very greatly, by a factor of 20 to 30, increased its metathesis activity. And we could now understand some of the work of Wan, because they had originally prepared that catalyst by mixing molybdenum hexacarbonyl with alumina in the air. There was no reason from the previous literature why you shouldn't. We just happened to be working in an oxygen-free atmosphere. And so, depending upon the amount of oxygen it got, it would influence its activity, which in their work rather wandered. But again, there was no reason they should have suspected oxygen, and we didn't know oxygen was going to do this. And then we were led to think, well, now if we take all the OHs off, then we can prevent this oxidation of molybdenum. So we tried heated alumina up to quite high temperatures. Rather to my surprise, it didn't lose much surface area, which seemed to not to check with what the literature had been. I think now that it just happens that we were deliberately working with a very pure alumina, which we'd gotten for other purposes in some work I was doing in collaboration with John Butt and Jerry Cohen on supported metal catalysts. PHF, American cyanamide, which is 99.99% pure. And in the absence of impurities, alumina is really quite resistant to sintering. You can start off with a material which is about surface area of 260 or so, and lose no more than about a third of its surface area when you go to 950. So this work started us on complexes on alumina, a little study of the tricarbonyl adsorbed species. Then more recently I've been involved with Tobin Marks. He thought that the idea of putting actinide complexes on alumina, and again our techniques were very lucky for this because these things are extraordinarily sensitive to oxygen. Say if you work on something with like this pentamethyl cyclopentadiene dimethyl thorium, in the presence of traces of oxygen, you're ruined. And on PHF, the protons of the OH groups just protonate the methyls, ruin it. So you have to work on a highly dehydroxylated catalyst to get anything interesting. Well, we just happen to be set up for that.
Did you get to know Kimball when he was working with Taylor, or was it later?
Oh no, he was there much after I was.
Yeah, but did you maintain contact with Princeton, or
Not much.
after you left, you left?
Not very much. I was now almost 1,000 miles from Princeton. I got back there very occasionally. Kimball I first met at the First International Congress on Catalysis in Philadelphia in 1956. And after that, we saw each other a fair bit.
Did you ever meet Polanyi to talk about his mechanism?
Never met Polanyi.
At Northwestern, there were always 3 or 4 people at least working in catalysis or related area, but there wasn't a lot of joint publications. Was there a lot of intellectual stimulation?
Well, when I was, in the earlier days when I was here, the only person, there was a Patiev, and then there was Selwood and myself. And Selwood and I talked quite a lot. It didn't lead, it led to 1 or 2 cases of cooperation, not very much. Now Northwestern does have, for some reason, has grown up with a tradition of a lot of collaborative research. But that was primarily after my early days here.
How do you interact with graduate students?
Now?
Or
When?
through your career?
How do I interact with them? Well, I talk to them. I generally have seen graduate students rather frequently. How much I intimately direct their research is dependent on the graduate student. I was always pleased with the graduate student who would do his own work and think of things and so on, and I would say, well, that's a nice idea, go try it. Or I could say, well, somebody already did that, or something like that. But I was very happy with students who would do their own work, and I've had some very much like that. Brenner was an extreme case. He wanted you to bother him as little as possible. I had to do it some anyway. But other students I've had who were a very independent type were people like Harold Kong, Cooper Langford.
What has been some of your great satisfactions in catalysis?
Well, one of them we've already mentioned. That was that methylcyclopentane affair. That pleased me. Another was the work that we did on dimethylacetylene, methylaline, and butadiene, because that, I think, opened up a mechanism. Or, yes, the idea of a dyed sort or a species or the equivalent wasn't, of course, novel. But some of the ideas there were put together so the whole system tied together reasonably well. I rather like that. And the molybdenum carbonyl work I've been pleased with, though I'm not sure anybody else has ever read it. But I guess well, the molybdenum carbonyl, because for most of my life I had studied catalysts invented by other people. But in the case of molybdenum carbonyl, we prepared the first supported metallic molybdenum catalyst. And that he was going to be a catalyst wasn't so obvious. It's still a bit mysterious. I still have people complaining about it. The general view being that molybdenum is so aggressive, it's immediately going to get covered with carbon and won't be a catalyst. And this sounds reasonable, but for example, you can take a metallic molybdenum catalyst and pass propane plus hydrogen over it for a large number of hours. It declines in activity over the beginning a fair bit, maybe losing 40% of its activity, but then it becomes very slow. And so the molybdenum doesn't fully understand this. And I think the whole question is probably the presence of hydrogen. In the absence of hydrogen, certainly molybdenum is very aggressive in reacting with hydrocarbon. But in the presence of hydrogen, this is somehow inhibited.
What is the most surprising thing that you've come upon in your research?
Oh, now, I have my friends who like to use the word surprising. They publish papers talking about the most surprising result. But I always say, well, if you're surprised, it means you weren't very smart. So that, surprising. Well, of course, if I don't know what the answer is going to be, almost anything can be surprising. But I think one of the most surprising things to me initially was these very sharp isotopic distribution patterns you could get with hydrocarbons, where it didn't seem initially very obvious why you should. Of course, later it's perfectly obvious you should, and it's no longer surprising. There was a writer in the early 19th century named Thomas Love Peacock, who wrote novels which were really comedies and humors. Most of his characters had just one characteristic which appeared throughout. And Headlong Hall, the squire had Mr. Milestone, the landscape architect, walking around the grounds. And he had with him another man whose only function in the book was to ask dumb questions or make dumb statements. So Mr. Milestone is admiring the landscape. And he says that in the landscape, he recognizes two characters, the beautiful and the picturesque. And the dunce says, well, pray, sir, but I recognize a third, sir. And pray, sir, what is that, sir? It is the unexpected. And Mr. Milestone said, and pray, sir, by what term do you designate it on your second tour of the grounds? So we can do the same thing in science.
And you're most frustrating.
I had a beautiful idea, very elegant. I was going to take silica gel, which is covered with OH groups, 5 per nanometer squared, and you can react things like silanes with them. So I could adsorb on the silica gel something that would absorb nicely. I took a compound with 2 nitrogens, one at each end of the ring, 1,4, and methyls, which I could put para or ortho, and I adsorbed these, and then I let the silanes react. So now I made a template into which the orthoxylene would fit, but paraxylene wouldn't fit. So I could separate them by absorption or chromatography. Never worked. Still don't know why. I think probably the grid was just not fine enough.
How did you start interacting with Budar?
Well, when I first met Budar, of course he was recently from Princeton. He'd gone to Berkeley at this stage. I don't know if I met him before that or not. But we met at meetings, and we had some common interests, and we started to talk, and just somehow or other, we seemed to have had a fair amount of interaction. For a while, we were giving a joint ACS short course on catalysis. We wrote a joint article. He did that. I mean, he was the originator in that, on mechanism in heterogeneous catalysis. And I guess it was just primarily because we got along well socially, and we had interests in common.
And who are some of the people in catalysis that you would consider leaders of catalytic science?
Today?
Well, when you were starting your career, partway through today?
Well, I guess at the time that I was starting, the major luminaries would have been Schwab, who was then fairly young, but already a luminary. He'd written his book, Katalyse from Standpunkt, what how's that go? Katalyse from chemischer Standpunkt aus, I think. Is that right? And I read that to practice for my German exam. And then there was, of course, Taylor, and Ely, and Sir Eric Rodil, and perhaps at that time, am I forgetting someone? I might have thought they were the leading people. Well, I guess already I should put the two Farkas brothers in this, because they were starting in the mid-30s. And I think Adalbert Farkas, unfortunately because his brother died young in an airplane accident, but Adalbert Farkas, I think, has been one of the keenest people to work in heterogeneous catalysis. And I think most unfortunate he didn't end up in an academic career instead of an industry.
Do you know why he didn't? Or?
I believe at the time he was trying, he simply couldn't find a job. It wasn't an easy period to find a job.
Did you ever interact with Ely?
Well, I knew Ely, and I visited Nottingham, and after he became an officer of the British Empire, I used to call him Officer Ely, which I think irritated him a little bit, not seriously. One time he claimed to be very angry with me. It was a meeting in Roermond, and the Dutch are very formal in these things, or were, and there was a banquet, and somebody gave a toast and a little speech to our foreign guests, and people from various countries gave a reply, and I was chosen to give the reply for the U.S. And so I said, well, now you know the Americans here, unlike the rest of you, have lost a day of holiday by coming to this meeting. It was the 4th of July that we lost, and said, now you people probably don't know what the 4th of July is, and I will tell you, it's the day we celebrate when English became a foreign language. And Ely put on a pretense to be outraged by this. Pure pretense.
Sir Eric Rodil, how would you describe him?
Well, I never knew Sir Eric terribly well. I knew him some, and but by the time I knew him, really, I saw him primarily when he was retired. Because after all, again, this was a matter, I never got to England until 58. But he was always a most genial person. And we had a meeting at Northwestern, which Herman Pines arranged for the 100th anniversary of Apatiev's death. And he was able to get some money for this, and he had some famous people, particularly Schwab, Ely, and Radil here. And I gave a little reception for some of the foreign guests at my house. And at a certain stage, maybe 10 o'clock or so, now at this point, Ely and Radil were both getting to be moderately elderly, probably almost as old as I am. And Taylor came over and said, "Well, Eric, don't you think it's time we go back to the hotel?" And Radil said, "Well, now, if you want to go, why don't you go? I'm enjoying myself. I think I'll stay." And he did.
And how long did he stay?
I forget now, but at least another hour. I think Radil liked to talk to people, just talk to them, converse with them, more than Taylor really did. He was probably more gregarious in that sense.
Obviously, then you learned most of what other people did by reading about it rather than traveling and meeting in person. How do you compare the two ways of communicating?
It depends upon the way your mind works. I do better by reading than by hearing. But in my earlier days, there was no choice. Maybe you had a visitor. For example, the first year I was at Northwestern, I just happen to remember this, we had 4 lectures by visitors. When did you get a visitor? When he was going through Chicago to California or something like that, and he was persuaded to stop off here for a day. But people didn't, in those days, cheerfully hop on airplanes and go around the way they did go today. There were no travel grants and contracts, there being no contracts or grants. Northwestern at that point, if you went to a national meeting and gave a paper, the dean would pay your coach round-trip fare, but that's all. So that just wandering around was much less common than it is today.
Yeah.
I mean, professors were usually here then.
How did you support your research and graduate students in your early days?
Well, Abbott of the Abbott Laboratories had given Northwestern some money that was jointly between chemistry and the medical school, which supported some research assistants. And the department had a policy, generally speaking, of giving one of these to newer, younger faculty members. For the rest, students largely supported themselves on teaching assistantships. And the department would try to make you could order chemicals and things from the general department funds. On the other hand, if you wanted any equipment, I spent some little time getting the department to give me a Type K potentiometer and a Podbielniak still. So that money in those days was much less accessible. On the other hand, generally speaking, research, a Type K potentiometer was a moderately piece of high-tech equipment. And the department had polarimeters and so on, and as things began to develop, of course, it began to acquire more fancy equipment. But when I came to Northwestern, there was basically nothing of what we would call high-tech equipment. I don't think there was almost anywhere.
And what do you see as the biggest change in the way the papers are written now versus
Well,
30s?
One is they're much more frequent. I think it was considered quite respectable to turn out 1 or 2 papers a year at the time I started. now you're supposed to turn out many more. Furthermore, when I joined the American Chemical Society in 1934, and I used to go to the mailbox hoping to get it, waiting for it to arrive so I could read it. And I would look at most of the articles and read many. Well, then came the pressure for conciseness and consolidation and so on. So a paper today is half the length of one then and twice as hard to read.
In what sense?
Well, they're so concise. I mean, you could read many papers if the author was a reasonably good writer. In the 1930s, you could read with some pleasure. Today, you could hardly say you get any pleasure per se out of reading a paper. It may be interesting, but just as reading, it hardly could be said to be a pleasure. The more concise, the harder it is to read, despite what editors will tell you. In a good writer.
Who had the most impact on the work that you did?
Well, in catalysis, the work of Kemble and myself, I think it would be fair to say, we mutually stimulated each other. He certainly stimulated me, and I think I stimulated him, but I will speak just for myself. And the work of Farkas influenced me. Since at this stage I was really trying to apply organic mechanisms to heterogeneous catalysis, some of my stimulation came more from outside heterogeneous catalysis than from within. And there, one of the people I was particularly interested in was C.K. Engel. In later periods, I became interested in inorganic mechanisms, and that began to develop. And since a fair share of that was done at Northwestern, I was exposed to that from the beginning. And so that I was influenced by Pearson's work.
How would you describe Pearson?
How would I describe it? Well, first of all, let's see. If you met him, it would be not immediately obvious that he was so important scientifically as he was. He didn't, particularly when younger, put on any atmosphere of this. He'd done his entire career at Northwestern as an undergraduate and then as a graduate. As a graduate student working with Ward V. Evans, and then he was employed during the war when some teaching needed, and there he was, and Northwestern had a rule that we wouldn't promote to tenure position anybody who had Northwestern PhD. So he was shipped off to Oxford for a year on a Guggenheim, and then the dean ruled that took off the Northwestern curse. And he was made a professor. But Pearson had ideas. He was very quick in catching on to things. He was very inventive in interpreting them. And he was good at presenting them, either written or oral.
Did you ever meet Wheeler?
Auburn Wheeler?
Yes.
Oh yes, I knew Auburn Wheeler.
And how would you describe him and his work?
Well, Auburn Wheeler's scientific impact came entirely from his work in diffusion. And that was certainly very influential in catalysis. It made one realize, first most important thing I think it did, in the academic rather than the industrial sense, it made people realize they'd better be careful, that you could get yourself very confused signals if you were having serious concentration gradients. So that I took Wheeler's work very seriously.
Did you get to know him well? Or?
I know him fairly well at Gordon research conferences and things like that. And he was always an amusing chap when he wasn't misbehaving and getting excluded from the Gordon Research Conference by George Parks, for example.
And how did he get excluded, or?
I'm not sure that we're ready for that story. George Parks himself, of course, later got excluded.
For different.
For a different kind of peccadillo.
How well did you know Emmett?
Well, again, I saw Emmett scientifically at meetings and so on and talked with him a lot. I wouldn't say I ever knew him terribly well personally. I don't know that Emmett was very easy to know terribly well personally.
In what sense?
Well, he also was rather reserved. I mean, if you classify, is he somebody you can gossip with over a mug of beer? That isn't Paul Emmett.
Who are some of the people in catalysis that you personally gossiped over a beer with frequently?
Well, I think, for example, you could do that with Farkas, or at least I could. And you could certainly do that with Wheeler, but not over one beer. And Emmett was very serious, I think. He devoted himself to heterogeneous catalysis. And he wasn't so much interested in small talk and things like that, in my feeling.
Did you know Otto Bake?
Know him? Yes. In the sense that I'd been to Gordon Research Conference where he was. I'd only knew him in scientific meetings.
So you didn't, how much did his work impact what you did?
Not very much, because it really wasn't closely related to what I was doing. On the other hand, that's not to say zero. The idea of, he was, I'm sure, the first person that led me to think seriously about carbonaceous deposits on the surface of metals. But, of course, Bake's total publication was just 2 or 3 papers. They were important ones, and none of them were ever really finished, hardly, speaking in a full sense. But he had ideas which certainly were important, and one of his major ideas, I think, that influenced me was this idea of the difference between a clean metal surface and one that was covered with carbonaceous residue. So, of course, if you carried Bake too far, you would never expose your catalyst to any reactants because it might make them dirty. But there was a period where it was a bit boring at the Gordon Research Conferences, where Bake and some of the other side would argue back and forth between my clean catalyst and your dirty catalyst.
Well, I saw recently someone credited Dowden's 1950 paper as being one of the things which most influenced catalysis in the last 50 years. How would you respond to that person?
Let's see, what happened in which 1950?
That's the one where he came up with the electronic...
Isn't that a Faraday Society meeting?
Yes, but then he published it in the Journal of Chemical Society, the one with the Fermi energy level.
All right. That particular work has never affected me. I don't think in any of my papers I have ever talked about such matters. I particularly never really quite believed the early semiconductor theories. And as time has gone on, I don't know that I regret it. There was a fad for a while to make everything into a semiconductor that wasn't a metal. And I think I always had a hunch that chemisorption was a local process, not a delocalized process. So that I was never, it wasn't, I guess at the time I couldn't have said I didn't believe them or given any arguments as to why, but I always thought I thought more chemically than as a physicist. And I think that as time's gone on, even the physicists now, in many cases, will treat chemisorption as a local matter of local orbitals, not as a matter of delocalized orbitals.
Well, in the early 50s and for some time afterwards, the catalytic cracking and acidity dominated probably the number of papers published. You never seemed to go that direction.
I published one paper on, oddly enough, the reaction of, primarily was concerned with the reaction of optically active 3-methylpentane, which we mixed up isotopic exchange, racemizations and things. But I generally have tended to be made nervous by bandwagon areas. I think if, gee, all these people are doing this, what am I going to be able to contribute? So I've been happiest, generally speaking, when I was working on a subject that was not in the bandwagon area. Now, of course, that has some advantages. It has a disadvantage that usually nobody's very much interested in what you do. And funding agencies don't tend to be, they tend to be more impressed, I think, in general by bandwagon areas generally. Although I've had people in these agencies allege that isn't true, that they'd rather not, but that's what they get for proposals. So that I, generally speaking, have gone into bandwagon areas sometimes, but only much later when the bandwagon stopped. So I didn't touch deuterium in the early bandwagon days, came into it later when it was calmer. And it's true that recently I've been collaborating with John Butt and Jerry Cohen for a while on things of structure sensitivity supported catalysts, but that was a collaborative matter in which we agreed there were some things we thought we could do. But ordinarily I worked in an area that has not been in the fashionable line.
What do you think are some of the things that have the biggest impact on catalysis since 1930?
Well, now, of course, I guess I would say that in 1930, what did we know about catalysis? We knew some descriptive chemistry of chemical reactions. We could tell you how to hydrogenate something, how to synthesize ammonia and methanol, things like that. We knew something about kinetics. But no one, except Langmuir, had yet really tried to give a mechanism. And so mechanistic thinking didn't really start until the 30s. I make exception to Langmuir, who was sort of an isolated genius in that sense. And the things that have helped studies of mechanism, probably most important thing, has been the introduction of isotopes. I guess I could say that. There are other things, obviously, but the newer things, people had already tried to interpret kinetics by then. Langmuir is the first person to have done it in the modern sense. One of the things that certainly has had a great impact on catalysis are analytical techniques. And just the ability to analyze. A gas chromatograph, I think, has had a tremendous impact on catalysis. Not to speak of, from the point of view of following a catalytic reaction. Then, of course, in 1930, there had been well, basically we could say no work on catalyst structure. And nowadays probably people go overboard on it. There's now more work on catalyst structure by a lot than on catalysis. And these have been made possible by a variety of new techniques. X-ray was really just beginning to be applicable to such things, or being used at any rate, and since then we've had infrared, EPR, XPS, all kinds of things, surface science. Now, there are three areas outside of catalysis that have had a strong impact on catalysis, because catalysis hasn't done much. I won't say zero. There are a couple of important things it's done in giving ideas of chemistry. One of which, though it had no impact outside, but was first done by catalytic people, was the idea of such things as surface alkyls, which even Sabatier had. But the reactions you mentioned on strongly acidic catalysts, all the ideas there came from outside of catalysis, from Whitmore and people like that, and they were applied in catalysis very nicely. And so that's a major influence, I think, in catalytic mechanism, and even beyond that in applications to some extent. Another area, of course, is surface chemical physics or surface science, because it can do things with single crystals that one can't really imagine doing in a heterogeneous catalyst. It's still most unfortunate that there's no way in which I can study the surface cleanliness of a supported catalyst by the kind of techniques the people in surface chemical physics use, Auger or XPS, for example, or yields, because all of those things involve sooner or later moving electrons, and they require high vacuum, and they can't get into the pores more than 15 angstrom, 20 angstrom units perhaps. But the ideas from surface chemical physics have certainly had an influence in the area of metals. So far they're just starting on non-metals or oxides and such things. But metals, they've been very influential. But one of the areas I think that's had a major contribution to ideas in catalysis has been, in general, organometallic and coordination chemistry. And so now I'm confronted sometimes on coming in one ear of the surface chemical physicists telling me that they're going to solve all their problems on catalysis by metals, by working with single crystals, and the other ear I have an organic or chemist telling me they're going to solve them all by going up to bigger and bigger clusters, starting with small ones. And it's not clear yet which will be the most important. I suspect surface chemical physics, but I'm by no means sure. They probably will both contribute.
Well, if you look in your crystal ball, catalysis was on the ascent for a long time. Has it reached the peak and is on the descent, or is it still going up?
And it'll go up again. There's nothing, science changes its views on fashions as much as in ladies' hats.
And if you were a young person starting in catalysis today, what would you try to start in?
I have just finished a postdoc, and I've gotten a job at University of X, and you asked me what I would work in?
Yes.
I think I'd work in oxidation catalysis. My thought being that maybe there's a little more novelty there. Now, it's not I say that that's necessarily the most important. I think it's important. But one thing I do feel about heterogeneous catalysis is we don't have many catalysts when you add them all up. And I feel in my bones there ought to be a lot more catalysts than there are. On the other hand, if I were a beginning assistant professor, I would be very nervous about searching for new catalysts. I'm afraid it would be a 5-year death if I hadn't hit one. But maybe when you get older, you can afford to do it. And in my older age, I've been associated with two novel catalysts. One came out just from our work, the metallic molybdenum on alumina, and the other the organoactinides on, and now organogermanium compounds on alumina.
It seems to me that catalysis in Europe developed more along academic lines than industrial lines, and in the U.S. it was the opposite. Is that a...
I think if you say petroleum industry, you're correct. Because after all, in Europe, we had the Haber process. They discovered the synthesis of methanol. They were the first persons to make margarine by hydrogenating vegetable oils. There was a fairly substantial industrial, but it was all in the chemical industry. It just so happened that the United States had the oil at this time we're talking about. It had the oil industry, and it had the major consumption of gasoline. As long as the demand for gasoline was much less than the demand for heating oil, which was true in Europe, there wasn't much push to go into modifying oil, petroleum. The United States had that well before Europe, so that Houdry, who discovered catalytic cracking in France, had to come to the United States to get it applied. Now things have changed. I mean, Europeans drive cars as much as the Americans do, but for a period the Americans, the demand on the American petroleum industry was different than that on the European petroleum industry. So that, if you put that into the industrial gas, if you exclude that from the industrial, I'm not sure.
Well, how did the Burwell lectureship come about?
That was a wild idea of Amico. They were thinking of making some little contribution to the catalytic community, and they got the idea of supporting a lecture series. What led them to name it the way they did, I haven't the foggiest. They claim it was just because they'd gotten so used to having me around, because I've consulted with Amico since 1949. I had to look it up. They asked me, when would I first come to Amico? And I said, for heaven's sakes, how do I know? Look it up in your files. All those files that old have been destroyed. Well, just by chance I could find it, and it was the 15th of January 1949. So I have been in Amico a long time, and somehow or other that led them to do it. But I'm not the man to ask why, because I don't know.
How did you get involved with Amico in '49?
Professor Somerville decided that I might be good at that, and he talked to some of his friends, or at least one of his friends there, and they were somehow bamboozled into doing it.
And who impressed you in catalysis work there, since people in industry seldom get their work publicized outside?
Well, there have been a number of people there who've done some fairly interesting things. Just to name a few, one of the earliest work was their development of was called ultraforming. It was a modification of Hensel's platforming, but they developed that rather cleverly, and it was used significantly for a while. Several people were associated with that, like Herman Seelig and Keith McHenry and some others. For a long time, I had quite an intimate relationship with John Perry, and I was always impressed by Perry as a very competent scientist. And there have been other people down there who I thought now, some of them, I mean, primarily their job is to do things that are useful to either Amico or on the one hand, or Amico chemicals on the other hand. And some of them, I think, have shown talent in that direction. Now, they haven't tried to do primarily academic research. But, for example, there's Harv Klotz, who discovered the Amico borosilicate sieve with the pentosyl structure, which has done very well for Amico.
What do you see as the difference between academic and industrial research in catalysis?
Practical use. I mean, I can study isotopic exchange between deuterium and optically active 3-methyl hexane, but I don't think any industry could be justified doing that. I'm never asked now, what money has this made or something. But finally, in industry, I asked if it has two problems. They can ask, the money we put in research, are we getting it back? Or they can ask the question, is the research we are doing going to make us viable in a few years? Now, I don't think that last question gets asked as often or as strenuously as it should because of the economics of the American system. The average manager is not judged on whether he makes it possible for the company still to be working 15 years from now. They hardly ever ask anything more recent, more farther back than last year. So that a very short-term push is there. Partly it's a question of effect on the stock market. But still, finally, under any system, even the Japanese, who apparently will push things for 10 years, or Bell Laboratories, which certainly did once, even there, finally, you need to justify your existence, your salary on the basis of practical economics. And the university person isn't asked to do that. Well, you've been in both circumstances. What's your reaction?
I would agree with that one. Some professors try to train other professors to produce a lot of people in academic work. Have you intentionally tried to direct students?
No, I've never tried to direct students because there are enough difficulties with the academic life, so I don't want it on my conscience that he went there because of my push. If he goes there, I've been quite pleased. But I've certainly never pushed anybody in that direction.
Did Taylor intentionally try to get people into academic world, or was it accidental in his case also?
I don't honestly know. I think Taylor liked people in academic life. But on the other hand, most of his people went into industry. I can't answer that.
What do you think made Taylor as successful as he was?
Hard work, imagination, drive, and a high level of self-confidence. I don't think he much worried about whether this was going to be good or not. He knew it was going to be good. It usually was.
Oswald was called by some the minister of propaganda for physical chemistry. Did you see Taylor as that for catalysis during his period? Or?
Well, I don't think Taylor had very much overall influence in the United States. He always remained a British subject, never became an American citizen. He became a Fellow of the Royal Society and a Knight. He hoped to become a Fellow of the Royal Society. That he became a Knight, I don't think he originally expected. Therefore, he was never a member of the Academy of Sciences. He was never really active, as far as I know, in the activities of the American Chemical Society. And there were people who resented his staying an Englishman when he was living in the U.S. Now, I believe Taylor always expected to retire to a little cottage in Devon. But unfortunately, he had two daughters who married Americans, who were the apples of his eye and grandchildren now. And so he never did. But I think this hindered his influence in general in the United States. And the number of people who followed in his line academically is not large. John Turkovich, myself, in the United States now, period. Boudar. Campbell claims to have been strongly influenced by Taylor, but then he's in Scotland. But Boudar, Turkovich, myself. Are there any others I'm forgetting? I don't think so.
We'd probably have to get a roster.
But, so I think that Taylor's total scientific influence in the United States